Yeah, sorry, kinda lost connection. I kinda lost connection for a minute over there. Uh, I hope my audio is still fine.
Yeah.
Yeah, cool. Uh, um, yeah, I think I have started recording. Yeah, recording is there, and I'll share my screen as well. Mhm, mhm. Yeah, cool. Um, I'll I'll hide this window. Mm, Yeah, so I'm assuming the terminal is clearly visible to all of you. Guys? Yeah, cool. See, I can't see the reactions. Realize that you have to speak up. I can't keep switching windows. That's very annoying. And like Infinity Mirror, it takes a lot of my CPU power. Because there is at the end of the day client side rendering as well for that. Anyways, yeah, see, CPU spikes up when that happens. Uh, Canaries, right? So I'll compile this again. So I think it was Harsha Kartikeya who asked me last time, why 6, right? Uh, huh? Oh shit, no, no. Uh, so this is why it's uh wait, where are the arguments for this? Uh, GCC, what? Oh, I compile. Oh, my bad, my bad. Uh, example. Yeah. So, as you can see, so turns out this is also a convention. Uh, ESI is RSI and EDX is RDX. We are just loading it so that, so the reason we are using the 32-bit registers over here is so that the instructions are small, because we know for a fact that our values are fitting within 32 bits. Yeah, who's that? What happened? Yeah, can you like mute yourself, Kartikeya? Cool. Uh, yeah, so what was still can others confirm? I think it should be fine right now. Yeah, so guys, is my audio clear? Unironically asking, like, and just say yes or no. Is it or not?
It's clear.
Yeah, cool. Like, I think there's some bit of interference, but there's literally nothing I can do about it. Like, microphone should be fine. So, anyways, I'll just speak a bit louder. That's fine. Uh, these the so yeah, for R8 and R9 we use the D prefix to indicate that we want to use 32-bit variants, and for these ones I think the E prefix is fairly straightforward for you people right by now. So in all 5 registers we load 1 because that's what we are printing, and then we push the remaining 3. So I think Harsha Kartikeya isn't here, but like he asked, right, why 6? That's the last thing that was on the
Yeah, I'm
stack.
there.
Yeah, that's the last thing that was on the, and he left. Perfect. Long story short, that was the last thing that was on the stack, which is why six uh, six was the right offset. So if I had to do which one did I, file.c, right? Yeah, I compiled file.c. So the first thing I did is print the address of win. There is a reason why I did this, and there is a reason why this isn't really needed as well. The second thing I did was uh, take the input to the buffer, then print the buffer, and then take the input to the buffer again. So in the first scanf, I give the format string to leak the canary. The printf leaks the canary for me, and in the second scanf, I overflow the buffer to return to win. Uh, cool. So I'll just explain the script now. Exploit. Yeah. So Poon Poon Tools is like the bread and butter of our thing. I'll show you a very nice blog that I found recently. That guy is very well respected in the community as well. If I got the link right, it should, yeah. No, this link I'll share it in the chat as well, and mostly I'll put it up in the description as well. This should have a section on Poon tools, but like it's a really amazing blog overall anyways. Yeah, it's slightly slow internet sucks over here. Yeah, actually, unironically peak, not even joking. So yeah, it has pretty much everything and more that I can teach you. But like, yeah, not so beginner friendly. Because it expects things and you can just see all of this. So it has packing. Packing is something we have used so much. Yeah, so context is, we can set the Poon context, which will basically now it will just use big Indian. P64 is like for 64-bit. U64 is unpack. Flat is, yeah, regular packing. I mean, you don't really need flat, but like fine. Um, Processes and communication, we have already used a lot. Process, this one, we're using it here as well. There's a reason I use PTY, that's because of my terminal, so some stuff goes on. Any case, I think this is all. Who is it? Okay. So I think this is all fairly straightforward. You can read this obviously in your free time. I'm not asking you to read this right now, and there are other features as well. I really recommend you go through at least the Poon Tools section for this. I right now I'll just explain the script here. So this is what's starting the process, and like the binary. The binary is out dot slash out, and that's this. So this executes it as a child process, and then we receive a line which is the address of the, what do you call that, function win. That was the first output, right? I'll show you. Okay, one second. I think file dot, yeah. So the first output. So the first output is. Does anyone know how to make this thing like an open meeting or something? It's kind of annoying to for me to like settings, general, desktop notifications, audio, video. Yeah, it's fine. Light. Anyways, so first line is win. Second is we take the buffer. Third is we print the buffer, and fourth is we take the buffer again. So I hope everybody remembers this sequence, because first we take the target. The target is the win function, which is where we have to go. Now we receive that as a sequence of bytes. So we first convert that to a string. This is a byte object in Python, and this is a string in Python. The two are slightly different things. Anyways, that's once again that's not really relevant. Like you don't need to learn a lot of Python to understand what's going on. Just like have a rough idea of syntax. This is saying translate it to an integer in base 16. The syntax is fairly straightforward. And yeah, you can reassign to different types. This is not like C or something. So Python is pretty flexible with that. Now the next thing we do is we convert it into a byte object again, but like this was some, like it's not this exactly, like this was a textual representation, and this is the, like, that was a sequence of four, let's say 0x4, it was 0x43, right? Let's say that was the sequence. This will convert, like that came in as text. So backslash x 00, backslash x whatever the ASCII value of x is, backslash x whatever the ASCII value of 4 is, and backslash x whatever the ASCII value of 3 is. That is how the text came in for you. But now what you finally want is this, like 0x43 is what you want as a byte. So that's what, okay, one second. So that's what these three things are doing. So first string, convert to string, then from the string convert to an int, from the int convert to a packed. So it's called a packed
uh,
struct.
like my internet went bad, so could
Hmm.
you like explain from the start, because like the connection went in the between.
Yeah.
I'm really sorry, I couldn't maintain
Yeah,
it.
yeah, 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 fine. You understand how seven came, right?
uh, like that is the exact point where it went.
Oh my God. Fine. So see, the six was, so you heard the part where I said six is the first thing, last thing that was on the stack, right? Before printf was called.
To be honest, no.
Just perfect, man. Okay. Yeah. So example. So what it's doing is it's just printing 8 integers using printf. So as you can see, the first 5 arguments are in registers. Okay. Now ignore the register names. They are taking 32 bits. That's not relevant here. What's relevant is that they are in registers, right? So and the sixth argument was the last thing on the stack. That was the sixth argument was the last thing that was on the stack before you did a printf call. Makes sense, right?
Yes, yes.
So okay. I hope I'm still connected. Yeah. So basically percent $6 p will be the last 8 bytes on the stack. So 7 will be above that, 8 will be above that, and so on. That's the generic idea of like the offset. You asked that the last time. I think I gave a very vague and dodgy answer this time. And like if you want to manipulate the registers, one, two, three, 4, and 5 are also available. So you can manipulate these registers as well. But let's not go there right now.
Okay, so
Uh,
basically, like the sixth one would be the top of the stack while printing. So, like you're thinking about the sixth variable in the stack.
Yeah, yeah, yeah. Now we do 7 here because sixth is the buffer, and right above the buffer would be the canary. I'll show you the disassembly. That's fine. But like you get how this is coming, right? Like six is buffer. If you print it, you'll see whatever you input. Cool, Harsha.
Yeah, you were saying something about the buffer being six, and like I mean, it was size 8, right? If I'm not wrong.
I'm saying sixth argument on, like, sixth argument for printf, not six of size. Size is 8 only.
Okay, okay.
So like in the 8 byte chunks, the first 5 are registers, and the sixth one is the last 8 byte chunk on the stack before printf was called.
Okay.
Yeah. So right above buffer would be the canary, as we already know, because I have like it's fairly. I'll show you the disassembly regardless. I think I compiled this with GCC. Printf. No, no. What was this? File.c hyphen o out. Yeah. GDB out. So yeah, I'll show you through this assembly. So basically, this is the pointer to the buffer, and so this is where the buffer is. So RBP minus 0x082, RBP minus 0x10. That's the buffer, and as usual, your canary is RBP minus 0x8. We'll come back to this, don't worry. But first of all, so next thing is, I shared a link in the chat. I'll share it again in the group as well. That is a very good guide to Poon tools. Anyway, what this is doing is, it's starting the process inside Python, inside this script in particular. And since the first line of, like, I personally choose to follow the order of whatever they are sending. Like, I don't, you can choose to not do it, but there are chances of deadlocks, so I choose to do that. Anyway, so the first thing is, I get the address of win function, which I print deliberately. I will do it without printing this as well, don't worry. Second thing is, uh, I I receive that as a byte object. So what is a byte object? So if it's 0x43, I receive it as \x00, which is the hexadecimal for 0, \x, whatever is the ASCII value for x, \x, whatever is the ASCII value for 4, and \x, whatever is the ASCII value for 3. That's what I receive in my buffer. If I have received 0x43 in text, I will receive this as bytes. Okay. I mean, this is just functions that, like, I'm just explaining what the functions do. Then I do a decode which does nothing but convert it to English. Uh, yeah, a string. So an English string, a Latin one string to be precise. So now it becomes quote unquote 0x43. It's a string now, and we'll see when it prints. Then the int function does nothing but convert it to an integer, because obviously, and like, this is the base. So base 16, take the string and convert it to an integer. Now what this does is, it packs that integer into an 8-byte object. So once again, it's a byte object, but unlike the previous time, this time it will be \x43, which was what we intended from the very beginning, but we received it differently. So all of that is what we did just to pack it into this. So, like, obviously, like, 8 bytes, but you get the point. Then we send the format string. This is here, that's 7th. From that, I put underscore foo as a marker to identify that this is my canary, because, like, oftentimes you will be blind printing stuff till you, like, get something reasonable. Then once again, I do the same business, decode it. Once it's a string, I split it at the underscore so that I get the canary separate and foo separate, and then I have the canary as a string, and then I do the same thing with canary. Once again, now canary is like the byte object after both of this. Then RBP, because right above the canary is RBP and the target. So this is the payload. The format string, you can fill in anything at this point, because the format string has done its job. I chose to fill it again. Then I send the format string and I print whatever it receives, which is the win function ka thing. So now I'll execute this. Oh, fine, my bad. I mean, I did not put the shebang. That's why. Okay, interesting. Yeah. So there are occasional instances where the canary will fail, and I will tell you why the canary failed in this case. Do you see 0D? Guys, are you there, or like, am I disconnected or something?
Where?
Yeah, so what do you think what do you think \x0d is? I mean, it's 10. That's obvious. I know it's 10. Like, don't give me trivial answers, obviously. This is 10. But why can this cause problems? Any guesses? Any guesses? This is a very observational thing that you need to keep in mind when writing your own exploits, shell scripts, shell code, whatever. Like, whatever you are inputting, you need to make sure there are two things that are not there. One of them is 0xd, the other one is 0x0. If you have an entire byte of 0, or if you have an entire byte of 0x0d, you're messed.
Like
Okay,
some kind of result, right?
it's it's okay. Uh, I'll show you in Python. Uh, So do you know what this is? And do you know what this
Data.
is? Yeah, not I
Yeah.
mean carriage return and this is new line. So these two things
Yeah.
and like this also, like there are a couple of things that you need to avoid in the input because these cause problems. Why they cause problems? As soon as you give a carriage return or a new line, scanner stops taking input. So technically your input got over somewhere over here itself. Where is it? Uh, okay, I can't find it again, but like so yeah, there are occasions where it won't work because the canary is that way. But then again, there's nothing you can do. Just run it again. Most likely it will work. So I hope exploiting using canaries is clear to everyone. How you overwrite a canary basically.
Yes. Yes.
Like there is nothing you do. You basically find at what offset from printf the canary is, print it out and read the value. That's quite literally what you do in a canary canary exploit. Anyway, yeah, that should be it for canary. Is there any doubt with printf format string? Mm, I am assuming none, so I'll move on.
No
But
problem.
like, yeah, cool. I'll move on. So now I'll show you how this all started. Uh, these were the resources I used to teach your seniors. What? Oh, okay, that's one. These were the resources that the pods learned from. Uh, 1 second, canary, right? Yeah, this is very interesting. Uh, so I'll first of all print the file. Uh, as you can see, I am not printing any address over here. Uh, so how do I get the address of the buffer? Any ideas? Have you all been using a tool a lot on because I asked you people to learn how it's done, how it's used. I asked you people to install a script for it as well. I hope you remember that, and I hope you installed that more importantly. Jeff,
Yes.
Jeff, yeah, GDB. So you okay? My bad. First of all, GDB. What is a canary? Okay, I will tell you what the flags are. Do not bother about it. And oh, I think I picked the wrong example, but fine. What you want to do is, I'll show you the exploit now. So first of all, okay, never mind. I won't show you the exploit. I'll first show you how to get the address because you need the address. Why you need the address? So once you come here, yeah. So this is the buffer pretty much. Like you, it's not relevant how I found it out. Long story short, this is the buffer because this is right above it. The 64-bit string, 16 bytes. 16 bytes, yeah, 16 characters, yeah, 16 bytes. 16 bytes is above this. This is 8 bytes, and this is the RSP, which is there for padding. Like otherwise, it would have been the last variable is usually where RSP is. This is for padding and a stack alignment to 16 bytes. Anyways, uh, this address, right? This address is what I used to find this address is what I used to find the buffer, but not exactly that. See, oh my bad. The thing is, in fact, I asked you people this question some time back as well. Why? What did I copy? Okay, never mind. So the thing is, who's texting me right now? Give me a second. Uh, so the thing is, uh, GDB will not give you the exact addresses for the stack, and just for the stack, assuming you have like, so there's something called ASLR which will come to, assuming ASLR is off, assuming pi isn't there, so GDB won't give you the exact address, but it will give you a decent range, and most likely within that range will lie your actual address. So what you can do is just run it on a loop, run it in a loop and find the actual thing. uh, so what I'm basically doing is I am using that buffer, I'm using that buffer to execute some instruction. uh, so I'm basically filling that buffer with instructions and executing it. Don't worry about it. I'll cover it up. Uh, yeah, I picked up a very bad example. But what I wanted to show you was this idea effectively. You can use GDB to find an approximate range of the variable. This is when you don't have the source code, obviously. Uh, Find the approximate range of the variable, uh, and then just brute force in that range. Uh, so if I have to show you, can read on py. Yeah, this failed, this failed, this failed, this failed, this failed, this failed, 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 failed. I have a feeling all of them will fail. Could be that. One second. Yeah, perfect. Okay. Failed, 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 failed. Yeah, quite a number of them are failing. But I hope you get the idea. I think I messed up somewhere. One second, what was the mm, this is in E1, okay, E8, right? I need somewhere higher, so it should come up eventually. Yep. So yeah, it took some time, but like I finally have a shell. Usually the function gives it to you. This time you had to put it there in a sense yourself. So, oh, next time also I got a shell. Wow. Sometimes things just happen. Oh, third time. Wow. Okay, failed finally. Oh, I think okay. Wow, interesting. So we'll come to what I did. Uh, Eventually, not now. But I hope the idea of like having a rough range and brute forcing in that range is clear to you. Yeah, cool. I hope that much clear. Now let's see. I wanted to teach what else? Printer format, string, shellcode. Good, yeah, shellcode. Okay, first of all, before shellcode basics. Uh, so spawn shell.c. So I think I have shown you execv before as well, right? Execv or execve, one of those two. Long story short, it does nothing but replaces your current process with another one. Give me a minute, guys. Yeah, sorry about that. Some important. Uh, so yeah, exec v basically replaces the current process with the process that you're specifying here, and in this case, we are specifying bin slash bash. Um, now on slash a dot out. Yeah, see, it's spawned bash. Uh, no, uh, shellcode. Yeah. So shellcode.c. So, uh, do you understand what's happening here? Those of you who have done C a lot might, but I doubt. But still, try. Think of what is happening over here exactly.
You're basically defining a function
Yeah,
like in the on
yeah,
the stack and then calling it.
yes, yes, yes. So, what this sequence of bytes is doing is, one second, give me a minute. I'll format it properly for you people to understand what's going on. This is the so this is an array of characters. So it's a string which is holding random bytes, not so random bytes. This is we label it shell code. Now, what is this thing? Do you all know casting in C? Typecasting. Fair enough. I'm assuming all of you are familiar with it by now. So what this is I say shellcode is a pointer to a function which returns an int and takes in nothing in the argument. And I bind that to ret. So ret is also a pointer to a function which takes in nothing and returns an int. So the thing about function pointers is you don't need to dereference them to execute them. You can just do the bracket thing and call them directly. Yeah, go ahead, Anvesh. Anvesh, was that accidental or like was that a doubt? Okay, I am assuming that was accidental. Okay, sure. No response. Okay, please, please. Yeah, so long story short, what we are doing is we are treating it as a function, this entire sequence as a function, because at the end of the day, instructions are also something like this only in memory. So why should we discriminate? Uh, and then we call it. Okay, so is this clear? Like, is there any doubt in this at the moment? Any doubt at all? Like, please ask.
Could you
Yeah,
explain the part where you're typecasting it to int star? Like, what does that
yeah.
exactly do over there?
So right now, what is it? A cat star, right? Harsha.
Yeah.
Yeah, yeah, yeah. So now let's see the type on the right hand, left hand side. Yeah. So ret is the name of whatever we are doing. This means it's a function with zero arguments, and this just means that it's a pointer, and this means that it's returning it. See, there's literally nothing else I can do about it. It's just syntax. But like long story short, this means ret is a function pointer that takes in nothing and returns an int.
Yeah, left part is clear, but the right part where you're converting shellcode.
Yeah, so this is nothing but the type of ret. If you think about it carefully, I just removed the name ret. The rest of it was the type. Isn't that what you
Okay,
people
so
do?
you're converting the string into a integer pointer. Is that?
Not integer pointer, a pointer to a function that returns an integer.
Okay, yeah, yeah, fair. Understood.
Yeah, so now the thing with C is you don't need like to dereference a pointer to execute the function. That's just something that the compiler accepts. So like it's not, once again, syntax, there's nothing you can do about it. So ret can just be executed. So I will finally uh, Shellcode.c information. Okay, ignore the .cargo/env not available. That is something that is picked from a bash RC, but you see, this is bash.
So is this shellcode in like the opcode of your processor, or is it like different?
Your opcode of what?
Your processor, like instruction set?
It's it's assembly, and this will work on like all in Intel and AMD processors, 64-bit Intel and AMD processors. So
Okay.
so the way it's generated is something like this. What you do is you write. So like you remember, I showed you basics, right? Uh, Spawn shell, yeah. So you take some program like this, something like this. You compile it into assembly. So basically, whatever. So execv is a freestanding thing for most part. So something similar is what you do in assembly, compile it, and then you have a very small shell code. Now this is one of the smallest ones that I have known. I think where was it? Shell code, right? Yeah, shell code. This is one of the smallest ones that I know. Uh, this is 24 bytes. Yeah, yeah, fine. So it was 24 bytes. And yeah, that's it. Like this is one of the smallest ones. I think the smallest one that is out there in existence is 23 bytes, but it really does not matter. If your buffers are those small, I don't think you can do much, to be honest. But just as facts, I'm putting it out there. 24 bytes is like one of the smallest shell codes. This does nothing. Like there are very complicated shell codes as well. Things that will like open up a port, bind to it, join to your interface, stuff like that. And there's like a whole bunch of things that's happening there. But this just gives you the shell. That's it. There are some that even give you a root shell. This is giving you a user shell. So now with all that done, let's see rect to shellcode.c, because this is where the fun part begins. So the very first thing I do is I print the address of buffer. Yeah, like kinda bad, but like I print the address of buffer, and now I will come to the thing in canary that I did. Uh, so I print the address of buffer, read into it, and for some reason I print it again. I think I was just printing it to verify that it was printed correctly. So why do you think I am printing the address of buffer? Can you like take inspiration from shellcode? Just the example that we just saw.
Yeah, so we would enter the shellcode in buffer, and then the address which we got from the printer will return to it.
Yes, yes, yes. So when we override the return address, we override it with the address of the buffer itself, which we got from printf. And then when execution gets over, we return to the buffer, and the buffer contains our shell code. So our shell code is getting executed now. Is that clear? Like, is there any doubt in that part?
No, it's clear.
If possible, could you please repeat it once?
What part?
The part where you were telling like the essence of why you're actually printing the address of the buffer and stuff. Yeah.
Yeah. So you remember how we did the overflow, right?
Uh, yeah.
What did we overwrite? Whenever we did an overflow, what did we overwrite?
The return address.
Yes. And now this shell code thing is something that can execute and give you a shell, right? That we have established.
Yeah, yeah.
And where is that? And if we are placing a shell code, where are we placing the shell code?
In a different file.
A, when we give an input here, where we place the shell code here. See, you can't open a different file. Relatively speaking, you can't open a different file and get the content. So whatever is happening through input output. So when we give a shell code as an input, where is it going? There's only one place it can go in this file, at least, in this code at least.
I'm not really sure.
Yeah, no. See, what is a shell? Okay, what is a shell code first of all?
It executes a shell.
Yeah, that's fine, but like, what is it in actuality? Like, it's sequence of bytes, right?
Okay.
So what do we give as? So now what we did here was basically execute the shell code. We return to the shell code. Do you get that?
Yeah. What does the string exactly mean or here?
This is the shell code. The instructions in binary format. So each instruction that you see in GDB. Okay, I don't have a. So these are all addresses, right? Now these themselves have some hexadecimal encoding. Okay.
Okay.
Now we picked one such hexadecimal encoding that gave us a shell, and we call it our shell code, and we put it here as a string. Now we want to return execution to it. So this is like C syntax, but if you had to do it in assembly, you just had to change the return pointer to wherever the shell code was, right?
I followed up to the point where you open GDB.
Bro, what? See, every instruction has a hexadecimal equivalent, right?
Yeah.
This hexadecimal ideally should also have some instruction equivalent, the way we are putting it out.
Okay.
What is that instruction set doing? Giving us the shell. Somehow, magically, it's giving us the shell. Don't bother how.
Okay.
So now what do we want to do? We have these instructions in place. Initially, we had a function in place. Now that function was also a sequence of instructions. This is also a sequence of instructions, right?
Yeah.
So we do nothing but redirect to this. We overflow the return pointer such that finally execution returns from here, the shell code.
Okay.
Like in this example, I covered it with C syntax, but when I am doing it in Z2 shellcode, this is why I need the address to write it in return, to write it in RIP. All right.
Okay.
So once execution is once main returns, it will return to whatever is there in the buffer. And when we start executing the contents of the buffer, which is our shell code, we get a shell. Now I'll compile this. Once again, don't question me over the flags. Do I need no pi isn't needed. And what else? Uh, okay, address. So first of all, I'll do a regular invocation. Once again, 1 second. Give me a second. Yeah, fine. So this is the address. Uh, and So there are better methods, obviously. As I have shown you, you can just read the input and get the content and use that as the target. But once again, so I'll show you the script again. So shellcode is nothing but the byte sequence, just like in that script, in that C file. This is also a byte sequence. Then we have some padding because the buffer was 48 bytes. This is something you have to figure out from GDB. Then we fill in the RBP with Bs. Then we fill in the return address where we have to resume execution from, which is our buffer address itself. And we send it off. Any doubt in this? Uh, okay, what did I, GCC did I use that? Like no stack protector, yeah, this should be fine, right? Oh, okay. Mm, this is very weird. Did I copy the address correctly? Yeah. Did I pack it? Yeah. Mm. Okay, this is very weird, but like it was supposed to work. And in fact, it did work when I checked it. Now I have no idea why it is working. Is that taking input? Yeah, that's also taking input, right? Yep. Uh, one second here. Okay, anyways, I'll just rewrite it to shell P is equal to pool dot process dot slash. Oh, it took the uh, to shell code address equals p dot require line address is equal to address dot decode address is equal to int address 16 address is equal to and again I don't need this p dot send line. Okay, something's messing up inside that, I think, and I have no idea why, what or why, but like, uh, I'll frame this properly and check what's going wrong and then show you guys. But I think you people got the gist of it, hopefully. Yeah, I wanted to wait a second. What? That's it. Code, registration code. Zero. This one is a zero. Uh, okay, anyways, let's leave it for now. I will give you a proper example after checking it myself. I don't know what happened. It was working right before the session. No, not even joking. So, but at least you got, I hope you got what I was trying to do, right? I think Harsha, because
Yeah.
Harsha asked so many questions, it was pretty clear to everyone else. Anyways, so what I'm doing here is a similar thing, and I hope you all are making notes because, like, sure, video will be there, but canary.c. So I read the canary, and like this time the format string is a little bit funkier, and there are arguments as well. So yeah, and we do not have the address. So I get the rough address from GDB, and then I fill in the shell code over there and guess after that. But I do something even smarter. So this is the target I obtained from GDB. Then I check it in a range for every 8 bytes because it will always be at 8 bytes as we saw in GDB. Then there is the shell code as always. There is padding, which is for the buffer, I think. Yeah, there is a format string. So like yeah, okay. For padding was needed for one buffer and format string was a different buffer in the example. Once again, don't worry. Just see the code and run the example, and it will make sense. Then we start the process. We send the canary leaking string. Then we
In
receive.
format string, the 11 is because is it like generally the 11th position is what the format occupies in the stack? Is that
No,
it?
no. Usually it's the six, but if you look here carefully, it was there is a lot more stuff going. Like it's printed there, right? See, this is the format string, right?
Yeah.
But there is a buffer below this. There are three more numbers over here. So there's stuff on the stack. And uh, besides that, so this would be this would probably be sixth, seventh, eighth. Then 9, 10th also went somewhere. I have no idea where. I think padding. And finally 11th was the canary.
Okay.
Like I think I did this like 1 year back when I was a coordinator. That's when I created the example, and since then we have been using it. At that time, I just checked GDB and figured out where it should be. So like that's the most standard method, to be honest.
Okay.
Okay, cool. Canary.py again. So yeah, 11,
And
11 is like
one more thing, you said that you were trying to get the address from the GDB using brute force. Like, I mean, what was that about?
it's right here. No, see, this address is what is there in GDB. I'll come to why the address is inside and outside GDB differ. I'll come to
Okay,
that.
fine.
That only happens for stack and maybe heap. I'm not sure about heap. Never really noticed that. But like this is the address inside GDB for the buffer, and then I just check it for a range because I'm not sure. Now there is something smarter that I do, which is why I was getting a shell in many tries. So I fill the buffer with SS, then a bunch of A's, then canary, then the return, then RI, then RB, then the stored RBP, then the address of where I want to jump to, then this something which is a lot of bytes and shellcode. So this lot of bytes has a very peculiar property. 0x90 is called the no-op operation, no-op in assembly. So what do you think no-op does from the name?
Nothing.
Yeah, it does nothing. It goes on to the next instruction. That's it. You get that? So if I put a no op, and if I manage to hit a no op, it will move on to the next instruction, then the next instruction, then the next instruction, till the time it finally hits the shell code. So it's increasing my chances of hitting the shell code eventually. If I hit a no-op sled, it's called a no-op sled because like sled, you know, right? Sled, reindeer, sleigh, Christmas and all, sled. So it slides down this and finally reaches the shell code. The instruction pointer slides down the no-op and finally reaches the shell code. So my objective for secondary offset would be to land somewhere here. If I do that, I'm sorted. Any doubts in this? I have a very strong feeling all of you are extremely lost. Is that true?
No.
Yeah, you and Rishit and okay, yeah, you two for the time being. Apart from the two of you, is anyone very lost? Oh, Madan's here. I did not realize that. Anyways, yeah, who is very lost? Please be honest. I can go through all of this again. Only Harsha keeps asking doubts. At least he asks doubts. You people don't even do that. And then DM me. That's worse because like I can't explain in a DM. I can explain. Yeah, like you need to cover like at least 6 more videos before you start understanding what's going on over here. That sounds like a you problem. Others, my DCs who have been attending sessions regularly, is anything not clear at all?
The thing about payload, could you?
Yeah, okay, so this is just the buffer. Okay, once again, I found this through GDB. Harsha, is that
Okay.
right? Yeah, that's so. Then canary. This is the stored. This is the old RBP I'm overwriting. This is the return address I'm overwriting. Then a lot of bytes and the shell code. So my objective with the
So the number of like 256, is that just a large number, or was there a particular reason you exactly chose that many no ops?
large number.
Okay, fine. Yeah, yeah, fine. And just to be sure, you put canary in between it. So is your function going to use it somewhere later?
I mean, no, I have to see there was a canary.
Yeah, my bad, my bad. I understood, I understood.
Yeah,
Sorry.
there's a canary. I have to make sure the canary remains in its place. See, before this is just fluff for me. For all if there was no canary, this could have been all A's. Okay,
Yeah, understood.
but and the main part is this address should land somewhere here. And
Uh,
I
uh, the
yeah,
the
Kumbha,
specific place for canary is that number of no ops that you did, or like close by it.
what?
You were saying something that the address at which canary should be present is somewhere around that.
Matlab, yeah, the canary is, see, the base offset that we got from GDB is this, right? Now the canary is above this. At least itna above this. Okay, I think you're mixing canary and knob slide right now.
Yeah, yeah, maybe.
See, see this in two parts. First of all of this till the return address, okay?
Okay.
So now, okay, I don't remember why I did S plus A, but like 32 bytes plus That's just the buffer I'm filling. Okay.
Okay.
Buffer plus XYZ stuff, whatever is there on the stack, I'm filling it. Next thing is canary. I need to place the canary exactly where it is. Once again, I found this through GDB. I did not like do some voodoo magic and guessed, oh my god, canary will be here.
Okay, so like 32 is the number of bits you had to overflow before you reached your specified location where the canary would be checked.
Yes, yes. And what is right above the canary? Our old
Yeah,
RBP.
RBP value.
Yeah, old RBP. What is right above old RBP? The return
Return
address.
address.
Yes. So is this part clear? Just this half of the payload.
Yeah, and like how you found out 32 is the number of things you had to overflow through GDB.
Yes, yes.
Okay, like later, could you just show how you got 32?
Yeah, yeah,
I mean,
yeah.
after you're done explaining with this.
Yeah, okay. So now till address is clear, right? Now this is the second
Yeah.
part of the shell. Now this is the second part of the payload. So what I do is this address should land somewhere in between this range.
Okay.
Now what happens after that is it landed on a no-op. It will execute the no-op, move on to the next no-op, move on to the next no-op, move on to the next no-op, and so on till it starts executing the shell code. But do you see the advantage of adding those no-ops? There are so many of them, it makes it easier for us to hit them.
I'm sorry,
So
could you
even if
repeat the
like
last part?
Yeah,
if
yeah,
the
go on.
offset is if the offset is not correct, but we would hit a no op anyways.
Yeah, yeah. Basically, if you even if the offset is some random thing that's nowhere close to the shell code, because there are 256 no-ops, you can slide to the shell code and execute it. Harsha, what were you saying?
So like you're adding that number of no-ops after the address, like you're pushing the address into the stack and then you're adding a large number of no-ops.
Yes.
And like, uh, yeah, fine.
Okay, but like it doesn't necessarily have to have like the same secondary offset, right? Because you're starting the process again. So if your offset like for the first program was 10, for the second it could be 9. And when you did 10, you basically went over it. So
Offset of what? Offset of what?
like okay, you are brute forcing it so that like the relative location might be disabled. So
Okay,
you are
okay,
trying
okay.
to brute force it.
You're talking about a target, right?
Yeah, yeah.
Where the shell code finally lands. That's what you're talking about, right?
Yes.
Yeah, so first of all, I think what you're leading on to is ASLR. We'll come to that. If you turn off one security setting, the address will be more or less constant. Like it can offset by 0x10 in some random weird glitchy occasions, but otherwise it will always be constant. So take that as a gospel for now. Second thing is even
Okay.
if it changed a little bit like that 10 wala thing I just said, ki 0x10 offset glitch happens. I think it happened multiple times with me while I was like checking this again. The no-ops will take care of it. We don't need
I
to hit the
see.
exit. We don't need to. So just to be clear, this target points to the S at the moment. So the negative range is always wrong anyway. So it points here. I have to make like it should be somewhere in the positive range, which is why I have to continue so many times when I was doing that. Finally, when it comes here is when stuff is actually good for me.
So ideally, shouldn't I put my target like in the middle of my no-ops? So
Target, yeah. Like, yeah, the address in the middle of your no-ops. Yes, I was just too lazy to like change things. Like this wasn't originally having a no-ops slide, but I decided I should show you one, so I edited this.
okay.
Uh, okay. After this, are there any more questions about no-ops? because I genuinely think there is nothing else to ask a question on. I literally explained every single detail. Okay, okay. Assuming no more. Oh, uh, yeah. I wanted to do this, but like I didn't know how to. Anyways, assuming you all are comfortable with this, I'm going to give you a very big shock of your life. Uh, you all hate it when I open R note? Give me a second, guys. Yeah, cool. I was getting my board. So, do you all remember the good old days when you had a stack and a text section and
Excuse
you
me, I
were,
have a doubt.
yeah, go on.
What's the use of no op? If we could directly jump to the shell code, can we? Like if
See,
we know the
fine.
address of that.
I mean, do we know the address is the question? We know the range. We
Can
don't know the address.
Oh, okay, okay.
If we knew the address, yeah, sure. That's what we have been doing for so long.
So like you are using no op to kind of just brute force to that address. That's it, right?
Yeah, in crude words, yes. And making my chances better, basically.
Okay, okay, fine.
Yeah, so say hello to darkness, your good old friend. Now I'm going to introduce to you sections and segments. So sections. As you all know, now this is not in memory at the moment. This is like a disk. This is like a file on the disk. So this is a file. This is a saved file, the binary, like a dot out the file. This is that. It has sections. Needless to say, it has sections. Do you think it will have a stack? It's a file, mind you. Very responsive of all of you. Am I disconnected by any chance?
No, we just don't know if it'll have a stack or not.
Uh, okay, it won't because stack is a runtime thing. You don't need a stack on the disk. But it will have two more things. Uh, yep. So it will have two more things. So these are the sections. Needless to say, it has a lot of things. I will send you three very detailed blog posts on this. Because if I sit down and explain you myself, I think I'll end up either killing you or myself. It's very frustrating and it's very annoying to like keep talking about this. It's insanely annoying. So as you can see, it's not that straightforward. First entry, first of all, to demarcate the first entry is empty. There is no section in the first entry. The second entry is something called interkey. Uh, Do you know what an interpreter is? Have you all used the shell?
Yeah.
Yeah, that's an interpreter. Turns out even compiled binaries have interpreters. Hmm. Ah, so yeah. Now, do you see these flags? A A A A A A AX 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 W A W A W A. So A means allocate. So these are the things that will be. So when you call the binary, there will be memory for these things. So like the init array, it will be in memory and it will be writable. So W is writable. Fini array similarly writable and in memory. Dynamic writable and in memory. Dot got, which is one of the most important things, writable and in memory. Inter p in memory. Okay, I don't know what that I means. I forgot. Yeah, but interesting. I don't see that. EH frame is exception handling frame. Anyways, uh, so ELF has sections. So when you map those sections into segments, so so what happens is a lot of these sections have similar permissions, right? These will all be allocated and executable. These will all be allocated and executable. These will all be allocated and writable. So does it make sense to like load them into different parts of memory? Like extremely different parts? No, right?
Yes.
Because if you load them together, it saves the time of the loader. So if you were observant, which I know none of you were, I used the flag called minus v exec stack. So stack is not there on the disk file, but obviously it's there in the memory. And similar to every other thing in memory, it also has permissions related to it. So it will be writable, obviously, because if it's not writable, what's the point of having it? Second of all, it will have memory, so it will be an allocate. Third of all, do you think it should be executable?
Ideally, no.
Yes, that's the point. So we are not going into how this is enforced. The operating system does something. I can teach you, but you will probably die in the next 1 hour if I do. So yeah, the Z exec stack means it's a flag to the linker saying minus Z is like anything that goes to the linker. So exec stack means make the stack executable. Give me a minute. So what happens if it's not executable? Segmentation fault. So like a segmentation fault is a very convenient way for the operating system to say you make any stupid pointer related error and I will throw a segmentation fault. So in this case, what happened was I can in fact show it to you in GDB as well. Move apps, light. Yeah. Now we are doing a call RDX. So we are calling. So this call RDX is basically that what we did, right? The ret we called ret, right? This is what happening in assembly. So when we do this over, this was an address on the stack. The instruction pointer reached the stack and the stack was not executable. When it tried to execute that, boom, segmentation fault. Once again, we are not going into how this is enforced, just that it is. So is that clear to people?
Just one thing. So, like, the function return values or such which are pushed on stack are only executable if you put that minus z to the compilation process.
Yes. Which is why when
Okay,
we
and so like basically stack is by default not an executable thing.
yes.
Okay, fine. Thank you.
You also use F no stack protect, that's fine, but you also use F no pi. What was F no pi?
Coming to that, what do you think F no stack protector is first of all?
Like it doesn't allow you to overwrite stuff in the stack. Right?
No stack protector. See, no stack protector. What is a stack protector? We have done this already. Think about it.
Canary.
Yeah. So F no stack protector says no canary. Don't give a canary. Even if there is a threat of overwriting the return address, I don't care. Don't give a canary.
But you were writing canary in your payload
Not this
and you
one.
compiled
Not
it using no stack protect.
not this one. That was canary ka folder. This one.
Oh, okay.
Different. See, that's why I labeled it canary because I knew this would come up. So like over here, there is no canary. Okay. Yeah, I have to. Okay, it wasn't there. C minus the exec stack minus exec stack. That's no stack protector. Let's see shellcode was C minus. Ideally it shouldn't depend on that because I'm printing the address, but like I have no idea. I actually have no idea why this is hanging. Okay, never mind. That's very complicated. There's literally nothing in this. I don't know what's failing in this. Honestly, it was working. If you saw my shellcode history, you would have seen that I've executed it once already. It was working at that time. Now it's not for some weird ass reason, and it's very annoying as a reason to be honest. Anyway, uh, yeah. So F no stack protector, right? Remove the canary. Z exec stack, make stack executable. If stack is not executable, your shellcodes won't work. If canary is there, you need to use a format string to read the canary and then write it back in its place. Or somehow leak the canary. Recursive functions are a good way to leak canary because if you realize it, they always have the same canary no matter what level of function call they are at. So like if call has if rec has called itself thrice or four times, doesn't matter, the canary will be the same. It might be useful in some scenarios, but that depends on you. Okay, so you asked no pi, right? How does it?
Yes, yes.
Yeah, so Allow me to introduce to you one another mitigation. Position independent executable. What do you think the name means?
I can execute it without permissions, like sudo without permission.
What? No, it's
Like I can
posi-
execute it without the permission of chmod plus x.
no. It's position independent executable. So
Sorry, what?
you a position independent executable, and who's texting me
Oh,
right
okay.
now?
Position independent
Yeah,
execution.
not
Okay.
permission, not
No
permission.
relative location then.
Uh,
Relative location then.
yeah. Are all of you tired?
No.
See, I think you realized it. You lost the right to say no a long time back. You and Rishit both. Yeah, others. Are you people tired? Because see, if I start this now, you will be crying by the end of it. A position independent executable is nothing but you compile the binary in such a way. So what happens is the entire code section ना जो भी sections देखे थे अभी हम whatever sections we saw यहाँ पे अभी uh, a what's the name, there is no binary in this one between DC resources and this. Yeah, so all of these uh, they they occupy some position relative to each other in the memory, right? When they are on when they
Yes.
are on the when they are in the file, like they have some offset, like of in not exactly in this sequence maybe, but like this is the sequence in their table. Who's texting me? I'm so glad you people aren't able to see the notifications. So yeah, okay, coming back to this. Um, Coming back to this, all of these things will be relative to each other in memory, right? It's the same relativeness in the file as well. So when they are in on the disk and when they are in memory, they will more or less have the same offset. That is taken care of. And even across executions, all of them will have the
By disk, what do you mean exactly here? Are you talking about the stack?
no, I mean the file. I mean the goddamn file. There's a file called example, which I execute. That's when the entire example is loaded into memory, and then that executes.
Okay.
See, like it's a file, right? So it's on disk. Like
Yeah,
exploit.py. Exploit.py is also on disk.
SSD
But
versus RAM.
yeah, SSD versus RAM, quite literally. Thanks, Abizer. That's a good analogy. So example, no, it's not an analogy, actually. So example, disk, and when you do dot/example, RAM. So like this stuff happened because it was in the RAM. Now whatever is in the disk is loaded kind of in the same fashion in the disk, and no matter when, where, and how you load it to the disk, the offsets will always be the same. In the RAM, the offsets will always be the same. Are you guys clear about it? A long story short, chunk is the same. It's just moving in memory in different places. That's it. That's all.
Yes.
I I genuinely did not understand what you just said, but like I will show you. So these are sections. They give you something called segments. I am not explaining to you what sections and segments are. I will give you give you 2 or 3 blog posts of mine. So now in RAM, they become segments which have some scheme of loading that the Linux operating system takes care of. Okay. Now this is segment 1. Let's say segment 1, segment 2, uh, so yeah, now inside this segment 1 we saw those sections, right? They will again have the same sections. So one of them will, let's talk about segment 1 just for the time being. It will have interp dot interp. I really wanted to cover this, but I am tired and I think you're all just dead after this. Like this is information overload for you at the moment. If I cover this, you're dead. You're absolutely dead. Sorry. Then what else was there? Some other stuff. Let's say init array is here. Please ignore. Don't ask me what these are. They are just sections for the time being to you. So some chunks. So this is in some offset, right? Let's say it's at offset 0x100, right? So now this will always be constant. This offset always constant. It cannot change. It simply cannot. Okay, but you see these segments, right? So what happens to this is in the first, once again, I'm talking about a single segment right now. First time you executed it, let's say it started at address. I'm pulling numbers out of my ass over here. So don't badger me on it. It started here. I think these are in fact operating system level addresses. Like they are not even executable addresses. In the second time you executed it, it started at 0x8000. Once again, numbers out of my ass, nothing significant to them. The only thing it would be is that the last 3 digits will be 0. That's it. Only thing, like the base address, last 3 digits will be 0. Baki sare numbers out of my ass. Please do not take the numbers seriously, except for the last 3 digits. Okay. Third time you execute, it goes on to some FFFFFF or something and executes from there. So FFFF 000. Okay. So what NoPy does is basically tells the program, sit down. You don't need to change your base that much. Okay. So it gives the compiler an option. You do not need to generate a position independent executable. It's fine if you hard code the addresses. I do not care. As is it. Is that clear?
Yes.
Good. Because Pi does not do this. Pi is a property. It allows you to do this. So pi, if the binary is a pi, it means it can jump bases like this. Okay, it can. Pi is not the thing that is making it jump bases. Pi only ensures that it can jump bases. Is that clear now? That's a property of the binary. It's a property. Okay, like I have dark skin. That's a property. And like I am in my room and I'm the only one with the camera on. That is also a property. That's not a property. Me having my camera on is not a property, but me having dark skin is a property. I can turn my camera off just like this. And if I want, I can kick Kartikeya out of the call just like that. Or maybe Anvesh. Or maybe Madan, I guess. And the 5 other people I'm not seeing on my screen at the moment. Okay? These are not properties. Me having dark skin is a property. So similarly, pi is a property that allows the executable to do this. Now, just because you have dark skin doesn't mean, okay, never mind. This has to go on YouTube. Yeah, so pi is a binary, pi is a property of the binary. I hope people are able to understand what I mean when I say property. Pi is
Yes.
not the thing making it jump around, okay? That is the operating system. And that is where we come to ASLR. So the two of them go hand in hand but must not be confused. This is done by the operating system. This is done by the compiler. This is an act. You do this. This is a property. This allows the act to happen. So now assume that the binary was not position independent executable. Do you think the operating system would load it in a place where it in a different place from before?
No.
Exactly. That's yeah. I'm not tricking you. This is not a trick question. That is exactly what happens. If a binary is not pi, the code section and anything related to that we saw in the uh, uh, all of this that is loaded, this will be constant. So the function address is constant. Where is I can't see the dot text. Yeah, dot text constant, plt constant, pini constant, ro data constant. Does that make sense? So see, if it's not pi, ASLR can't do jack. Everybody's confused. Perfect. Now tell me what the confusion is. Harsha,
Yeah.
what's the confusion?
I'm sorry, I did not listen.
Perfect. What is, are you confused anywhere? So address space layout randomization is an operating system property. PIE is a binary property. So ASLR is done by the Linux and even Windows for that matter. PIE is done by the compiler. It's made by the compiler, and once if a binary does not have PIE, ASLR is at the moment useless. Does that make sense? Guys, I am genuinely curious. Is this too fast or too technical or anything like that?
It's all right.
Okay. Uh, so if pi is off, so I'm giving you a situation. and I'll ask a question about it because this is very interesting. Pi is off, but ASLR is on. So I'm calling out the first name I see on my screen, Sarfraz. Hoping you're in the meeting still. I said Sarfraz. Proxy पकड़ी गई. 0% attendance. No, so sad. Uh, am I audible? Cool. Anvesh, now that I know you are here, answer my question. I think from next time onwards you'll stop texting also. So if this is on, so I think we have established that the text section will be in the same address. Who's texting me? Yeah, so Anvesh, I hope you're still there. Yes. So we have established that the text section is in the same address if pi is off, right? Anvesh, yes. So what do you think happens to the stack? A few things to note, stack was not a part of the original file on the disk on SSD. It wasn't there on SSD. So what do you think happens to the stack? Is it still randomized? Is it not randomized? Could what do you think will happen? ASLR is on, pi is off. Guesses are fine, but like you can probably tell me the right answer. Like I have given you enough clues. Perfect. So pi means only dot text ka address will remain constant, and like related things, dot text plus related things. Uh, I hope you get my vibe. So this thing fixed address because well the way it's built means that it cannot be changed. Anvesh, is that much clear? Because pi is off. Pi off. Now ASLR off means nothing can be changed at all. Everything is in the same address for more or less part. Uh, right? So despite pi being off, stack can change its address. I hope that's clear to everyone.
Yes.
Yep. So do you think pi off and ASLR on gives you any advantage apart from just randomizing the stack? What else is there in the binary? Okay, heap, stack, heap, anything else? Anything else? Shared, maybe something. I don't know. People packed fast, damn. Uh, the answer is yes, and the thing is shared library, but we will not cover that now. So for now, this is it. Take a break, relax, and digest whatever I've done today. Last time I'm asking you, any doubts? I don't know what I digested. See, you will digest it slowly and steadily once you rewatch the video. And yeah, by the way, guys, if you have any doubts from previous videos, feel free to like drop a text in the group. I also got an overview. हाँ exact picture दी भी नहीं है bro. मर जाएगा तू. Maybe I need to rewatch it. I'm sure all of you need to rewatch it. That's not a choice. Like I'm telling you, you need to rewatch it. Yeah, 0.5x, perfect.
The last part where you told about pi and ASLR, is it possible for you to discuss it maybe in the next class once again? Because like at
Yeah,
the
yeah, yeah,
last part,
yeah,
I
yeah, yeah,
kind of missed it.
yeah. Bro, I know you. None of you would have understood it. I'm sure of that.
Okay, thank you.
Yeah, so that's it for today. Next time, please keep offline. See, you get me a recording apparatus, I'll keep offline. I don't mind. I can get a room also. I'm not even kidding. Like the room getting room is not that hard. Like both the profs whose approvals I need are profs who are teaching me courses, so they can always approve me. So that's not a problem. I just need like somebody to get a recording apparatus. And by recording apparatus, I mean a tripod for a phone. Yeah, that's it. Like
We can make
literally,
Richard stand there and hold the camera slash phone.
uh, see, but you need to do that. Like keep if you manage to keep it in a consistent position, I will take an offline session without my laptop. In fact, probably because there is nothing to show you for that one. All of that becomes very theoretical. Not very, but like I need to draw diagrams and stuff, so might as well just do it on the blackboard instead of that. So is that clear? Like, okay, it's not
Yeah.
clear. Obviously, it's obviously not clear today. Whatever I taught you, but I hope you people learned something. Canaries must be clear. Printf must be clear. Format string must be clear. Shellcode somewhat clear, I guess. Vibhu, Nisarg, Kiran, Sarfaraz isn't responding. Srimukhi, I need to go digest some food before I go through. Bro, I told you, eat dinner. I ate at 6. Oh my god. Wasn't hungry at 8. Now you must be very hungry. Dying by dying. Yeah, okay. So go eat food, chill. When your mind is fresh, rewatch the video at 0.5 and hopefully you'll understand. See, I'm assuming canary and format string must be clear because that was definitely covered by 9. Yeah. See, if that was clear, then it's fine. Everything else is extra for the time being. See. And shellcode is something that like you can figure it out on your own. So yeah, that's it for the meet. Any questions that are not like related to today's session? Yeah, bought some. I heard, I understood that perfectly. Bye. Vibhu wanted to say something, but I problem 14 Poon College. Hey, that one. No, that's some. I need to see that again. I'll reach out to you. I'm just very busy, man. Like I'm not even kidding. Uh, I'll reach out to you. Hopefully, sometime if I get time. Till then, like try to understand. See, you can do like you can do watch points in memory. Like you can do watch a memory point and then assign a breakpoint to it of sorts. If you just Google it, how to set up a watch point in GDB, you should be able to figure that out. Then you can see exactly it's a pi. That's fine. That's not a problem. But how? Wait, what? So that doesn't mean anything. Wait. Just set up a watch point in GDB because GDB does not randomize addresses. It will always keep the same address. Set up a watch point. Look up online how to set up a watch point and see where the address is being changed. Value at the address is being changed. It does that. GDB, yeah. In no way, bro. Then you turn randomization on for some reason. See, I don't like. There's a command to turn that off as well. Don't worry. So like, yeah, I'll try some shit. Yeah, sure, please. I'll cut. Bye.